Welcome to Mastering Solutions. To start this off, we've talked about this idea and a couple of the other questions. How I like to think of this is if we have a diffraction grating here, and let's not even talk about diffraction grating, we just have a single slit and we have light coming in and it gets diffracted off at some angle, right? We're measuring that based off of if the light didn't get diffracted at all, just went straight through. This is some angle there. Well, what is the maximum possible angle? We'll say, pretend that's M1. Let's say this is the angle for M2, some other angle. What's the maximum possible angle we could do? It's if it went along here and we had a 90-degree angle. That's the maximum possible angle that we can do. What's the equation for theta? It's sine of theta is equal to m lambda over d. But what is sine of the maximum possible angle we could do? If we said 90 was the max, sine of 90, you probably already know, is 1, right? So that is the maximum possible value that m lambda over d can be for us to see that bright diffraction order. So this has to be less than or equal to 1. So now when we go through here, we have a diffraction grating. Let's figure out what the d is. Let's see, we have 1 times 10 to the negative 3 meters divided by 500 slits. Remember, it's always width over slits or width over lines, same thing. And then that would give us some number. I'm not going to bother calculating it. And then we have the wavelength, they say, is 510 nanometers. 510 times 10 to the negative 9 meters. So what is changing in the equation? We're wanting to figure out how many diffraction orders are seen and what's the angle of each of them. So a way that we could do this, there's a couple ways, but the way I think is easiest is let's just start plugging in m values until we get one that's bigger than 1. If it's bigger than 1, can't see it. Let's see, we want to do m lambda over d, so m of 1 times 510 times 10 to the negative 9 meters divided by d, which we said is 1 times 10 to the negative 3 meters divided by 500 slits. Okay, so 1 times 500, whoops, not 500, 510. 510 times 10 to the negative 9. And then all that is divided by d, which you said is 1 times 10 to the negative 3 divided by 500. There we go. Okay. So that gives us a value of 0.255. So that is what the m lambda over d value represents. But to find theta, we need to take the inverse sine of m lambda over d. So we can take this and take the inverse sine of it, and that'll give us the angle for the other part of this. Let's write it down here for right now. So 0.255 is our m lambda over d. Now, I think it's easiest to do this way because in your calculator, I'm not going to write all of them, but you can have 2 times 500 times divided by d, and then 3. And so all you can do is just take this and just change this to 2. And now we have 0.51. So m of 2 equals 0.51. M of 3 gives us 0.765. And last one, m of 4 gives us 1.02. So m of 4 is greater than 1, so we will not see m of 4. So now if we take the inverse sine of all these, we have inverse sine of 0.255. So that angle is going to be rounded to 15 degrees. Then for M2, we have the inverse sine of 0.51. So that's going to be 31 degrees. And then inverse sine of 0.765 gives us 50 degrees. So we have 31 degrees for M2, and we have 50 degrees for M3. So for the last part of the question, you have to be careful because they want to say how many diffraction orders are seen, not how many bright spots are seen. So for this one, we will see 3 diffraction orders.